Okay. I'm glad to introduce uh, the second speaker, Ljubica Velimirovic. She will talk about shape and energies of geometric objects. Please welcome.
Thank you. Actually, I'm Ljubica Velimirovic from the Faculty of Sciences and Mathematics of University of Niš from Serbia. And I would like to thank to Professor Kaufman and to the organizers for inviting me to give a talk here at this conference. I hope that it will be at some place and we will meet there and have possibility to talk together. And also I wish to Professor Kaufman long, happy life, and I wish a happy birthday to him. I have met Professor Kaufman for the first time at Serbia few years ago, where he was the chief guest of Serbian Mathematical Congress, and also the guest of our late professor, Professor Slavik Jablan. Later, I have met Professor at Chicago and also at Novosibirsk and at Greece for the last time, but we stayed in connection for years, and we made some progress in our cooperation and have a few papers together, and also are working on our joint book with the same title like my today's talk. I want to speak about shape and energies of geometric objects and mention also knots here as a geometric object. I'm talking from a mathematical, from geometrical point of view. Actually, I'm professor of differential geometry, and I want to thank to Professor Kaufman that that wanted to come to our place to speak about geometrical knot theory and to work together with us on this topic from geometrical point of view. As we know, he's working for years from topological point. First, I would like to say something about motivation for our research, then about shape and energies, then about curves and knots, surfaces, and first, speaking about motivation, I want to mention the motivation for our talk and the book and for our cooperation. It is to analyze application of geometry and also topology in considering different shapes of objects. We find that the geometrical point is useful for considering tissues and cells, and we use geometrical topic curvature and its functionals to consider some very interesting topics that are related to some problems from biological process which occurs within them. Deep understanding of interaction between shape and biology has fundamental implications for our healthcare and is important in processes like embryogenesis, organogenesis, and also design and development of new materials for tissue engineering. In this way, we want to offer our geometric point of view, not to solve some biological problems. Maybe in cooperation with some other people, we can we can consider these applications. We provide source of inspiration to people working in biology and chemistry, but also biological problems inspire us to give some solution. Also, our consideration of shape and energy can be applied for architectural design. And we have considered something, but our work is also in progress in this way. We are included at one project that is European Curvature and Biology Network. And this is the place where curvature, like a geometrical object, a geometrical problem can be applied. This is some cost action that is interdisciplinary, and where researchers from biology, mathematics, physics, and material science are involved in research the interplay between curvature and biology. Main objective is to bridge a gap between these disciplines by helping researchers develop a common language to exchange ideas, and by training them in the use of state-of-art tools from cell biology and also from computer science, discrete geometry, and computer biophysics, for instance. This is the answer. What is the consideration of shape and energies for? And we are trying there to make some problems, and I will also mention some problems that are we working on from geometrical and topological point of view. The parts of and working groups at this European project is teaching then curvature and cellular membranes, then curvature and single cells, and so on and so on. So we are considering curvature. I am in a field of differential geometry, and for years I was working at Riemannian and generalized Riemannian space, but these problems of curvature that can be applied at, for instance, biology and chemistry are interesting for me nowadays, especially when I met Professor Kaufman and began to think about application of my geometric point of view at knot theory. We have made a book that didn't appear yet, and that is under construction, let's say. And this book has a few parts that are treating some of the problems I have mentioned. We were considering geometric point for considering variation of curvature and some other problems from energy and energy functionals. And the book is written as a monograph and is based on decades of our work, and has several parts. Some of them are included in my today's talk. The content of the book will be on shape and energies, curves and knots, surfaces, and shape and energies of knots, topological topics that are based on Professor Kaufman's research. Some relevant references are some very old, like Professor A.D. Alexandrov's on infinitesimal deformation on non-regular surfaces, or Viktor Alexandrov on the total mean curvature of non-rigid surfaces, then many others, or some new, like a note on infinitesimal bending of rectifying curve, and many other many other papers are relevant for this topic. There are some very interesting, like Professor Margareta Toda and her cooperators that are in the similar topics, and many others. What is the shape in this geometrical meaning? The shape of an object located in some space is a geometrical description of the part of that space occupied by the object as determined by its external boundary, abstracting from location and orientation in space, size, and other properties such as color, content, and material composition. We are considering rigid shape and also bendable, deformable shape. In geometry, two subsets of Euclidean space have the same shape if one can be transformed to the other by combination of translation, rotation, and uniform scaling. In other words, the shape of a set of points is all the geometrical information that is invariant to translation, rotation, and size changes. We are here mainly considering non-rigid shape definition, and say that non-rigid shape or shape of deformable bodies is very often in the nature, and it is more flexible, and we deal with deformable shape in reality. When we consider a person in different postures, positions, we think about, is it the same person? It is the same shape or not? Or when we consider tree bending in the wind, or a hand with different finger position, we are thinking about, is it the same shape? By allowing isometric deformations like bending, intrinsic geometry of the object will stay the same, while subparts might be located at very different position in space. This definition uses the fact that geodesics, curves measured along the surface of the object, stay the same, independent of the isometric embedding. If we consider, for instance, my hand, is this of the same shape like this, for instance? The distance from the finger to toe is the same as, in this case, as if we measure the distance going from toe to finger. With geodesics, the difference, the distance is the same, and we can say that this and that is the hand of the same shape. For instance, we can consider cell and can say that cell comes in variety of shapes. The shape reflects the function of the cell, and it is very important. For instance, here on the picture, we have nerve cell, and parts of this cell and this cell as a whole is in function of its importance and its function in our body. For instance, if we consider normal cells and cancerous cells, we can see that there is the difference in shape. It is very important to consider this difference in case of small deformations, to consider small deformations of cells to check the function of the body and the disease to control the state of our body. There are some questions about shape that are interesting. Some of these questions are for elementary school children, but some answers to these questions are very serious. And I will only put these questions and give no answers, but I think that all these questions are interesting to be answered and to be considered, also from scientists. There is a question, why are many fruits almost spherical? Or why are all stars and planets spherical, not cubic or tetrahedral? Why are raindrops spherical in shape and bigger drops flat? What is that the egg of various birds are oval shaped and not spherical? That is also the question of shape of soap bubble. And also shape of crystals, the question of shape of crystals. And there are many other questions, like a very important question, are all the cells in the human body of the same shape? How is the cell shape related to its function? What shape does the DNA occur in, and how is it changing shape? What does the change in shape of DNA means, and how is it related to the many other things in genetics, for instance? And the shape of curves and surfaces, geometric objects in Euclidean three-dimensional space is determined by their geometric curvature. Intuitively, the curvature gives the answer to the question how much a curve deviates from being a straight line, or a surface deviates from being plane. In the case of a circle, smaller ones bend more sharply, and so on and so on. In the study of shape of curves and surfaces, and also knots, it is useful to observe curvature-based functionals, and these curvature-based functionals are said to be energies of curves, surfaces, and also knots. We consider Willmore energy, torsional and energy, total curvature, total torsion, total normalcy, Möbius energy, different kinds of energy that are curvature functionals related to the curvature of curves and surfaces, and consider the change at infinitesimal deformations. First, we consider infinitesimal bending of the first and then on the second and the higher order, and consider also infinitesimal bending of knots and variety of energies in this case. What is the infinitesimal bending of a curve? If we have regular curve C included in a family of the curves C epsilon, where U is real parameter, and we get C for initial epsilon equals 0. Then we have that family of curve C epsilon is infinitesimal bending of a curve C if the difference of the squares of line elements is infinitesimal of the order higher than the first. Function Z is infinitesimal bending field of the curve. That is basic definition of infinitesimal bending. That is a small deformation where difference of the squares of line elements is infinitesimal value. Some very first papers are papers of Yefimov, and here are some questions of theory of deformations of surfaces considered, and here is theorem that necessary and sufficient condition for the field Z to be an infinitesimal bending field of a curve C is to be dr dz equal 0. And also there is a bending field for a curve C given with the equation 5, where we have some functions, and that bending field is given with this integral. And also in the theory of analytical functions by Vecqua, we have that under infinitesimal bending of the curve C, the line element undertakes a non-negative addition, which is the infinitesimal value of the order, at least with respect to epsilon, which is some small value, infinitesimal value. What about the geometric magnitudes under infinitesimal bending? The change of these geometric magnitudes under small bendings are described with variations by variation, and if we have geometric magnitude A that characterizes geometric property on the curve C, and the corresponding magnitudes of on the curve C under infinitesimal bending, then we have coefficients delta A, delta 2A, and so on, the first, the second, and variation of geometric magnitude A under infinitesimal bending of a curve. Here are on hyperbolic paraboloids some curves and their bending, and also what is going with the knots. We are considering knots as a curves from geometrical point of view. According to the definition, another knot C prime is equivalent to C if it can be continuously deformed into C without crossing in itself during the process. And we have, in topological sense, different knot types. But what is from geometrical point of view? From geometrical point in geometrical sense, we can observe particle representative of a knot type as a closed self-avoiding curve in three-dimensional space. The point of view has been of interest in many physical situations. Some of them I have explained, because a deformation like an infinitesimal bending has a huge application in mechanics, especially in the theory of shells, and here is C and knot theory. Here is an example. In geometrical sense, small deformations of knot can be considered as the family of different curves. We have a bending field given like Z equal, and it is an infinitesimal bending field for the trefoil knot. And we have infinitesimal bending given in this way. And for this infinitesimal bending field, we have that initial knot is included in family of in one moment torn curves, a trefoil knot, and infinitesimally bent, but torn curves. And also for different bending field, we have that the same trefoil knot can be included in a family, continuous family of curves, and we get for different values of epsilon of these small parameters curves that are infinitesimally bendings of the initial trefoil knot. Also, here is one other example where trefoil knot is infinitesimally bent and included in a family of knots. We can present a knot as a rope with some positive thickness, but self-avoiding curve. And also can consider surface defined by bending of curves. If we have curve C and deformed curves C epsilon, where epsilon runs to 0, and we have Z like infinitesimal bending field, then we can consider this continuous family in space and have a surface that was made like infinitesimally bending of this trefoil knot. And also, if we consider torus knots, we bend this knot infinitesimally, but go out of torus. And we have basic knot and infinitesimally bent knots in this case. And also the surface that is generated by infinitesimal bending for different parameters epsilon. I can say for these pictures that these pictures are graphically maybe not precise, not beautiful, but they are precise, accurate pictures, and we have associated considering knots and curves and surfaces graphically. There is one kind of energy that is Möbius energy. And if we had knot K in three-dimensional real space, Euclidean space, then the Möbius energy of this knot is given like this integral given with 10, where L of ST denotes the minimum distance along the knot K between points R and R of S and R of T. Möbius energy is given with A for knot K, and also like A of K epsilon for deformed knot. And in order to consider the change of energy during the bending, infinitesimal bending of knot K, we consider variation of Möbius energy in this way, given with equation 15. Also, if we want to illustrate this Möbius energy, we are considering the knot and the knot colored by the value of Möbius energy at the points of this knot. And this is given with the picture, and can be considered from different points of view. Also, we have this here, a knot and the deformed knot together. We have numerically calculated Möbius energy of the first order infinitesimally bent torus knot, and give for epsilon equal 0, and for it means for initial knot, and for epsilon equal 1.2 or some other. We are also consider the other functional of the curvature. It is a Willmore energy. Willmore energy of knot K is given like this integral of K square. Do you see correctly the picture? Sorry?
Sorry?
Willmore energy of deformed. Do you see the picture?
Oh, no, I just
I
see the
have some
definition of
problems with the. You don't have a problem? Do you have? No?
I mean, I'm
Maybe the
looking
problem is with my
Wilmore
computer.
energy. Yeah.
Yes, but something is moving on the picture. Oh, okay, you don't see. You don't
Uh,
have this problem. Okay, maybe this is with my computer, the problem. We have Willmore energy that is defined with 16, and the deformation of a knot, and the Willmore energy of deformed knot, and also in case of a knot K, we consider the variation of the Willmore energy given with 19. On the infinitesimal bending of a knot K, variation of the Willmore energy is given in this way with respect to curvature and torsion of a knot. And can be considered further for special cases of knots. We also consider total curvature of a knot K, and we say that variation of total curvature is given with 2022. It means the change of total curvature. Under infinitesimal bending of knot K, variation of total curvature is given with 23, where tau is the torsion of a knot K. Also, we can consider for a knot total torsion of a knot K, and we have total torsion, and under infinitesimal bending of a knot, we have the variation of total torsion. Here I'm giving only results of our considerations of um, uh, energy of knots, not discussing special cases like it is given at our papers, or that can be further developed and further be given. Also, we consider total normalcy of knot given with 26, like a function of a curvature and torsion, and under infinitesimal bending, small deformation of a knot, we have the variation of total normalcy, where k and tau are the curvature and the torsion of a knot. We also consider infinitesimal bending of the second order. We have given infinitesimal bending of the first order, and also can consider infinitesimal bending of the second order, where Z1 and Z2 are bending fields of the first and the second order. At this case, at infinitesimal bending of the second order of a curve, the difference of the squares of line elements is infinitesimal value of the order higher than the second. And this is the definition of infinitesimal bending of the second order, and the equivalent equations are given with 31. And we are also considered we also consider infinitesimal bending of the first and the second order of the curve, and have bending fields giving with 32 and 33. And at the case of knot, we also can consider the same things and see the variation of curvature and second variation of the curvature of a curve, or of the knot that is infinitesimally bent. We consider Wilmore energy. That is main descriptor of the shape of curves or of the knots. We consider Wilmore energy of the knot K given with equation 36, where K is curvature of a knot at a point, and Wilmore energy of deformed knot is given with 37. In this way, we can consider also the variation. It means the change of the Wilmore energy, the first variation and the second variation of the Wilmore energy of a curve or of a knot. And for the Wilmore energy under infinitesimal bending, we can say that on the second order infinitesimal bending of a knot, the first and the second variation of Wilmore energy are given with equation 40. Also, we consider total curvature given for the knot by equation 41. Total curvature of the deformed knot is given with 42. And also we consider variation of the total curvature given with 44. And according to these calculations, we have the theorem that under second order infinitesimal bending over knot, the first and the second variation of total curvature is respectively given with first and second, 45 and 46, where k is the curvature and tau is torsion of total curvature. And we have some figures. We have figure 8 knot and basic and infinitesimally bent for epsilon that relates to the bending field that is 0.75. And for bending knots, we have that the energy of these knots differs, and in this way we can study the shape of knots. Also, we consider torsional energy and can consider
Excuse me,
the shape.
Professor.
Sorry?
Sorry. May I ask you how long time you need more?
I can stop whenever you want. If I don't have
Yeah.
time, I can finish in one sentence. Is it okay?
Okay. Sure. Yeah. Please.
Okay. That is the way that is the way we consider shape and energies of knot by using different kinds of energies. We have mentioned some of them.
Mm.
These kinds of energies can be considered and discussed for special types of knots, special kinds of knots, and can be there are applications in the fields I have mentioned before can be considered further. Thank you.